Good morning. Today we'll be going through electric circuits. Okay, so an electric circuit is a closed path in which electrons move to produce electric current. Okay, and when electric current flowing from a positive to the negative, it can be used by an electric appliance such as a light bulb. So as electric current flows, the light bulb will then kind of switch on. Okay. So in grade 10, electric currents were introduced, and you guys were topics such as Ohm's law, voltage, potential difference were kind of discussed. And then in grade 11, power was introduced. And then in grade 12, right now, you guys are dealing with internal resistance, which is what we'll be working through in this past paper. Okay. So we are working through the Eastern Cape September 2022 past paper. It's downloadable. If you want me to send it to you, I'll be happy to do that. Okay. So we'll be working through question 8. Question 8 reads 8.1 says a group of grade 12 learners want to determine an efficient conductor which can be used as the heating core for a kettle they are constructing for their ESCOM Expo project. Okay, so let's analyze what we have. They say they conduct each of the three conductors. So they're looking for a conductor, an efficient conductor, in which they can use as a heating core for a kettle that they are constructing for the XCOM Expo project. Right? They connected three. Connected each of the three conductors. So you have three conductors A, B, and C in a circuit, and they measured the current, which is in our y-axis, as well as as well as they measured the current, they measured the current passing through the conductors in our y-axis and the potential difference across the conductor in our x-axis. And their results are shown in the graph below. Okay, cool. Current is then the rate at which electric charges flow in a circuit, and then your potential difference is the difference in electric potential energy per unit charge between 2 points in a circuit. Those are definitions. Okay, cool. So 8.1.1 then states name any two variables, right? Any two variables that must be kept constant for a fair investigation. Okay, so they're asking which factors affect the resistance of a conductor. And if we keep these factors, then we will have a fair test. So that's what we're looking for here. We're looking for factors that will affect our resistance. Okay, so what do you think? Okay, the first factor is temperature. Okay, we need to keep temperature consistent. Okay, Okay, so this is the first factor that we need to keep consistent is temperature, because if the temperature increases, okay, it has an effect on its resistance. So we need to keep temperature consistent. The second factor or the second variable that must be kept consistent is length. Okay, the length of the conductor. Okay, that has to be kept consistent because if it varies, it will affect the resistance. And the third thing, I know they asked for two, but the third thing could also be thickness. Okay, you need to keep the thickness consistent. Okay, cool. 8.1.2 reads, so just to go over the answers, temperature, the length of the conductor, as well as the thickness of the conductor, those are all the acceptable answers. Okay. 8.1.2, write down the physical quantity represented by the gradient of each graph. Okay, so they say write down the physical quantity represented by the gradient of each graph. It's very important to be able to formulate what's this thing, an equation from a graph. Okay, and this is from maths, right? We know that the formula of a straight line is y is equals to mx plus c. Okay, very important. You need to be able to create an equation based on the graph, and the equation of a straight line is y is equals to mx plus c. Okay, so if you have a graph, then you should be able to derive an equation. Okay, so we have Y, which is equals to our current, I, right? Okay, it's equals to M, which then will be our gradient, which is 1 over R x k. And then we know that X is equals to our voltage. Right, so this is then our equation. Okay, and then they ask us write down the physical quantity represented by the gradient of each graph. So from our equation, I know that my gradient is 1 over r, so that is equals to 1 over r. Okay. Okay, cool. Moving on, we have 8.1.3. Which one of the conductors is efficient enough to be used as a heating coil in a kettle? Give a reason for your answer. Okay, so now they're asking you have three options. You have A, B, and C. Which one of the conductors is efficient enough to be used as a heating coil in a kettle? And then you need to give a reason for your answer. Okay, so keyword here is heating coil. Okay, generally we're looking for conductors with low resistance generally, and we're looking for conductors with low resistance because we want to save energy when we pass current through a conductor. But in this case, we're looking for a current with a we're looking for a conductor to be used for heating coil in a kettle. So we need a conductor with a high resistance. So that's the first thing. We're looking for a conductor with a higher resistance. Um, if it has a higher resistance, it will convert more of its energy to heat. So we're going to go to the graph and look for a conductor with a high resistance. Okay, so a conductor with a high resistance will have a low gradient, right? So a conductor with a high resistance will have a low gradient because we know that the gradient is equals to 1 over r. Okay, so the lower the gradient, the higher the resistance. Okay, because the gradient is inversely proportional to the resistance. Okay, so we're looking for a gradient, we're looking for a resistor with a low gradient, and which one will that be, A, B, or C? And the answer will be conductor C. It has the lowest gradient. Okay, so the answer here is C. Okay, then they say give a reason for your answer. The reason is that it has the highest resistance produced. Okay, the higher the resistance of a conductor, the more heat it produces in the conductor if the current is constant. Okay, that will be your answer. Okay, cool. And that is 8.1. Okay, now we're moving on to 8.2. It says the circuit diagram below represents a combination of resistors in series and in parallel. I think we can spot them. If this is open, right, then current will flow through it. Then we'll only be considering these two, which will be in series. If this is closed, then we have two resistors in parallel. So we have circuit diagram below represents a combination of resistors in series and in parallel. Then they say the battery has an ELMF of 12 volts and an unknown internal resistance, right? So now, as I said, that this is now something that you guys will be looking at in grade 12, looking at internal resistance, and we know that batteries have internal resistance or any other voltage source has internal resistance, okay? And it's unknown, but we know that the total energy supplied by the battery is equals to 12 volts, okay? And then we don't know how much is external, and we don't know how much is the voltage, the total load, and we don't know how much is from the internal resistance, but we know the total is 12 volts. Okay, cool. So we have an amp meter of 1.5. Yeah, we have an ammeter reading here of 1.5. We have resistors, as I said, that if this is closed parallel, if it's open, we have these in series, and then yeah. Okay, cool. Oh, I need to. So the question reads, with switch S open, the reading on ammeter A is 1.5. calculate the following. So we have 8.2.1. It says total resistance of the circuit. So we're going to be calculating all of these based on the fact that we're going to be calculating all of these with switch S open. Okay, so we're going to calculate the total resistance of the circuit. We know that okay, let me write here. We know that I is equals to 1.5 A, right? And then we have an internal resistor, and we can't use V over I is equals to R, right? Because we have internal resistance, right? We must use this, okay? This is the formula we need to use, is equals to I R external plus R internal. Okay, so this is the formula that we have to use. We have this. We know that it's 12 volts. Okay, we have this. So 1.5. We can then calculate the total resistance. So we can calculate all of this. Okay, so then we're just going to put everything. So we're going to say 12 is equals to 1.5. And then we have R external plus R internal. Okay, therefore, then we're going to divide everything by 1.5 and divide this by 1.5. These cancel out. So then R external, which is our total resistance, plus R internal is equal to 8 ohm. Okay, so that's how we're going to calculate total resistance. Then they ask, calculate the internal resistance of the battery. So now we're looking for just R. Okay, calculate. I'm really sorry. Now let's calculate the internal resistance of the battery. Okay, so now we're just looking for R. So how do we determine external resistance? So we know that the external plus the internal is equals to 8 ohm, but now we're looking for the internal resistance only. Okay, how do we calculate R external? Because now we have two unknowns. We have to solve for one to solve for the other. We have to first solve for one and then solve for the other because we have two unknowns. So we're going to first work with external resistance. Okay, how do we calculate external resistance? We know that external resistance is equals to R series plus R parallel, right? Okay, so then what are we going to do? We're going to quickly analyze our circuit. Okay, we know that current flows from positive to negative, so it's going to flow from here. Okay, positive, flow this way, flow this way, flow this way. Then when it gets here, it could potentially split. Okay, current could split, but this is open, so no current is going to flow through here. So it's going to flow this way, flow this way, flow that way, and all the way back to here. Okay, so then we're dealing with, we only have our resistance only. Okay, we've only resistance in series. Okay. Okay, so then we don't have anything in parallel. Okay, so then R external is equals to R, it's equals to R, it's equals to series in resistors in series. Okay, so then the calculation then just becomes R external is equals to 3 plus 4. Okay, which is equals to 7 ohm. Okay, now we just have one unknown because we've solved for our external, so now we're just looking for our internal. Okay, internal resistance. So we know that R external plus R internal is the internal resistance is equals to 8 ohm. I know that this is 7 plus R is equals to 8 ohm. Therefore, R is equals to 1 ohm. Okay, I think that's how it's also kind of for. You have to first calculate your external resistance. Okay, because we have two unknowns, right? We can only have one at a time. Okay. Okay, cool. So now we're going to do 8.2.3. Okay, it says calculate the energy dissipated by the 3 ohm resistor in 3 minutes. What does the word dissipated mean? Okay, I think it's quite important that you guys search these things and understand what these words mean. Okay, so the word dissipated is it's a physical process by which energy becomes not only unavailable but it is irrecoverable in any form. Okay, that's what the word dissipated means, right? So it's a term that is often used to describe in which energy is wasted. Okay, so they're saying energy dissipated by 3 ohm in 3 minutes. Okay, so how do we calculate that? Okay, so to determine the energy dissipated, we need to know power. Okay, we know that power, okay, because power it's the rate at which electric energy is converted in an electric circuit, right? So we know that power is equals to work over change of time. Okay, but we also know that um, work is equals to no. So work is equals to power divided by change of time, and power is equals to work over change of time, and work is equals to power times change of time. Okay? No. To determine, I'm really sorry, to determine energy dissipated, we need to know work. That's what we need to know. We need to know the work done. Okay? And we know power is equals to work over change of time. So work is equals to power times change of time. Okay? Energy dissipated, we are looking for work. I really apologize. I was confusing the two. Okay? So with energy dissipated, we're looking for the work done. Okay? No, not the work done, just work. Okay? So we know that work is equals to power times change of time. We know that power is equals to I square times R. Okay. We also know that power is equals to V square over R. And we know that it's equals to V times I. Okay. There's a lot of thingies, a lot of formulas here. Okay. So we're going to just look at the formula where we know all of the variable. Okay. I know my current, I know my resistor. Okay. So this, I'm going to just use the first formula where power is equals to current square times resistance. Okay. So it all depends on the variables that you have. So you need to kind of choose a formula where you have most of or all of the variables that you need. Okay. So in that case, we know that work will then be equal to I square times R times change of time. Okay. And then we're just going to have to substitute all of these into, then we're just going to have to substitute I squared is 1.5 squared. Okay, that's what we have. R is 3 because we're looking for the power, the energy dissipated by the 3 ohm resistor. Okay, and they're saying in 3 minutes, but we know that we're working with seconds in physics, so we know we're going to say 3 times 60. Okay, and your answer is equals to 1215. And what unit is work? It's in joules. Okay, I'm just gonna quickly charge my laptop. It's about to switch off. Okay, cool. We are good. Okay, so those are the questions with switch S open. Okay, now switch S is closed. I'm going to quickly go back to our diagram. So now this is closed, okay, which means that current is definitely going to split because it's going to move through here, and then they kind of come back together and then move through here. Okay, so now current splits between these two, and then we definitely have resistors that are going to be in parallel. Okay, says with switch S is now closed. How will each of the following be affected? Right? Only increase, decrease, or remain the same. So that's all they're looking for. They're just looking for the answer: increase, decrease, or remain the same. Okay. Total resistance of the circuit. Well, the total resistance of the circuit, which is 8 ohm. So the total resistance is 8 ohm. Will, because now the circuit is closed, will the total resistance increase, decrease, or remain the same? Okay, so I think we can do a little quick calculations. If the current is going to split, okay, so now we have current is going to split, and now we have 2 and 3 are in parallel. Okay, so now our external is going to be equal to R series plus R parallel, okay, which is equals to your 4 ohm, which is in series, plus your 2 times your 3 over your 2 plus 3, which is equals to 5.2 ohm. Okay, before our let me quickly undo that. Before, our external resistance was equals to 7 ohm, right? Now that the circuit is closed, our external resistance is equals to 2 ohm, okay? Clearly, this is less than 7 ohm, right? So which means that it is going to decrease our total external resistance. Our total resistance of the circuit is going to decrease. So the answer here is decrease. Ooh, I can't find my content. Okay, I found it. Okay, the second question is um, I don't know what happened. I feel like I'm missing a question. 8. Okay, now it's going all the way to 10. Oh my goodness. I'm really sorry, guys. I'm looking for. Okay, I don't know what I did, but now I can't find my 8.3. Ugh, it goes all the way to 10. Okay, no worries. I'm going to quickly upload it again, and then we'll be back in business. Okay, but we calculated it clearly when the circuit is closed. The external resistance decreases, and I mean you can also calculate. You can say 5.2 plus 1, that gives you 6.2. So clearly that is less than 8. So you can definitely see that it definitely decreases. And here they don't necessarily looking for what's this thing, and aren't like a reason why. But if there was a reason, you can clearly tell them that the external resistance decreased, therefore the total resistance will decrease. Okay. I can't get it back. I'm trying to upload it. Okay, guys. I'm gonna try to resave this as something else. I think that's why it doesn't want to load. I'm really sorry. I'm gonna quickly just upload this and see if it works. Okay, cool, it works. Thank the Lord. Okay, so then we're gonna move to 8.3.2. I'm just quickly waiting for it to upload because The one I have doesn't want to. I think I clicked something. Okay, cool. It's ready. I think it's page 15. There it is. Okay, cool. Okay, cool. There it is. Thank goodness. Okay. So it says switch S is now closed. How will each of the following be affected? So now we did total resistance. Now we the reading of the um, ammeter. So will that decrease? Will that increase? Or will it stay the same? Okay. So we know that V is equals to I times R. Okay. So when the resistance increases, the current should also what? Okay, so we found out that the total resistance is going to increase. Now they're asking what's going to happen with the ammeter reading. Is that going to decrease or is it going to increase? When the resistance decreases, our internal current goes up. So it will increase. Okay, so where are we? So this will increase, and this will decrease. Okay, cool. So they say, now we're moving on to 8.4, a conducting wire, okay, of neglectable resistance is now connected between X and Y, okay? A conducting wire of neglectable resistance is now connected between X and Y as shown in the diagram above. What effect will this have on the temperature of the battery? Write down only increase, decrease, or remain the same. Okay, so I think let's quickly look at this. So now that we have, they say that, so now they've attached this. Okay, they've conducted a conductor, and its resistance is probably quite small, so we don't have to consider it. And now they're asking us, and this is now closed. Okay, and now they're asking us, what effect will this have on the temperature of the battery? Okay, if we connect X and Y, we have reduced resistance. Okay, so we've connected X and Y with reduced resistance because it's neglectable. So X external has decreased. Okay, what consequences does this have? Okay, as we have mentioned up here, if this decreases, then our total current is then going to increase. Okay, so this has gone down, this has then increased. Okay, so V internal is equals to I total multiplied by R. Okay, okay, so this has then increased. Okay, it's gone up. So then, therefore, our internal voltage will also increase. Okay, so work done by this will then, so the work done will then increase, therefore the temperature will also increase. Okay, I hope that makes sense. Okay, so I think the main thing with internal resistance is that now we can calculate it, or yes, we can calculate it. And I don't know, you remember the formula I mentioned that we're going to start using because there's internal resistance is, let me, oh, I won't be able, it's this one where we say is equals to I R plus R, because we have internal resistance, we have to consider it. Okay, I think that we can maybe quickly do another question. I was hoping that I can cover another topic as well. So I think we will kind of maybe do sound waves. I want to cover as much as possible so that you guys kind of get a lot from this and you better prepare for the exams. Okay, so this is it. I think we'll do another question. Okay, so that at least with these sessions we cover different questions. I think, yeah, I think let's quickly do, maybe let's do question 6. So now we have done electric circuits. We have spoken about internal resistance. We have spoken about things that affect, things that to consider, and no factors that affect your internal factors that affect resistance. Yes, we've spoken about factors that affect resistance. We have spoken about internal resistance, and I think, which is the new topic that is introduced in grade 12. I think that we should kind of move on and do another topic, so kind of cover another topic as a whole instead of, and then moving forward when we start doing revisions, we'll just cover more questions regarding internal resistance. Okay, so we're going to quickly go through question 6, which is now your wavelengths. Okay. Okay, we're going to quickly go through question 6. If we have time, we're going to do another question of electric circuits. Okay, so, or I'm not sure. I'm now thinking maybe I should kind of go through electric circuits again. So go through another question paper so that you guys can have like more. Uploading the wrong thing. This is the marking guide. That's okay. I'm gonna quickly upload the right thing then, which is this. Okay, cool. We're gonna quickly go through another question. And then if we can, start with your wavelengths, your sounds, and light. Okay, cool. I think it's also gonna be around question 14, I think. Yep. Just the question. Okay, cool. So, question 8.1. Elena sets up a circuit to determine the and internal resistance of a battery. So, this is the objective. They're trying to calculate those two, and she has set up this circuit. Okay. She uses the results obtained to plot the graph shown below. Okay, so there's usually a graph. First question is kind of like a graph, and then we move on to other things. Okay, cool. So first question says define the term to amp of a battery. So now it's just definitions. So what is the definition of that? It's quite important. You can score yourself a good 2 marks if you guys kind of remember the definitions. And mostly with physics, some of the definitions kind of help you to understand the equations as well. So the definition is the total energy per coulomb of charge that a battery can supply. So the definition is the total energy per coulomb of charge that a battery can supply. So that is the definition. Okay. So 8.2 says use the graph to determine the alpha of the battery. And that's just 1 mark. Okay. So we have what? We have potential difference in our x-axis as well as current in our y-axis. And they say you determine what's this thing? Use the graph to determine the alpha of the battery. Okay, so if you're gonna use that, we know that it's right here. It's 1.4, 1,4 volts. Okay, calculate the internal resistance of the battery. Okay, say calculate the internal resistance of the battery. We're looking for this one over here. That's what we're looking for. Okay, so we know that this is, we're going to calculate it using gradient. Okay, as I said before, if you have a graph, you need to be able to kind of create, what's this thing? You need to be able to create an equation. Okay, so we're going to say, we know that y is equals to mx x, okay, I guess we could say plus c. It starts up at 1.5, maybe plus c. We know that y is our potential difference, which is in voltage, and then we have our gradient, and then we know that x here will be our current, okay, and then we have our gradient, which is then going to be equals to over time. It's equals to our charge. This is what m is equals to, and this is equals to, okay, so this is what our gradient is equals to, okay? Calculate the internal, and we're going to calculate it using our gradient. This is our gradient, and then we have 1.4 minus 0 over 0 minus 2.5, right? 1.4 minus 0 over 0 minus 2.0 minus 2.5, okay? And that is equals to negative 0, comma 5, 6, okay? Our gradient is equals to negative r, which is equals to negative 0. Ooh, my 0 looks like 0.56. So our resistance is then equals to 0.56. Okay. Next question says, that's weird. Goes, oh, yes. Okay. A circuit is connected as shown below. The resistance of R, which is connected in parallel with the 4 resistor, is unknown. Okay, so we have this resistance connected in parallel with the 4 ohm, and it's unknown. The battery has an alm of 15 volts and an internal resistance of 0.5. When switch S is closed, the voltmeter reading is 13.5. Okay, so calculate the reading of A, calculate the reading on ammeter A, and then calculate the resistance of R. Okay, so how would we go about calculating the reading on the ammeter? Okay, it's quite 6 marks. So there's a couple of steps that we're gonna have to do. Okay, so this is how we can go about it. Okay, so we can say V internal, right, is equals to this, okay, and we have all of it. So V internal. So we're gonna first calculate our V internal, okay. So we have 15 given, right, minus, they say the voltmeter reading, okay, is then 13.5 when it's closed, right. So then V internal is equals to 1,5 volts. Okay, we know that our R internal, right, is equals to V over I. So we have 0.5 is equals to 1,5, which is what we just determined right now. Okay, we know that this is V internal is equals to, this is from this, where we say V internal resistance is equals to IR. This is, we just made R the subject of the formula. Okay, cool. So we say R is equals to V internal, right? Okay, over current. Then we just calculated. I hope I'm not confusing you guys. I hope it's making sense. Okay, we calculated V internal, 1.5 volts. Okay, I know that V internal is equals to my current times my internal resistance. Okay, and then I have my V internal, I have my current, I'm looking for my internal resistance. So my internal resistance is equals to my V internal divided by my current. So we have, we're looking for current. Sorry, man, we're looking for current. Okay, because we're looking for the reading on the ammeter. Okay, so internal resistance 0.5, because that's also given, right, is equals to V internal, which we just calculated, which is 1.5. Okay, we're looking for the current. Cool. So therefore, our current is equals to 3A. Okay, but this is the current based on our V internal. Okay, now we're going to calculate when it's in series, because it's in series though. Okay, so our current 3 amperes. Okay, but this is not the reading here. The reading here, it's when it's connected to the 4 ammeters in series. Okay, so we have voltage in series is equals to I times resistance in series. Okay, it's almost like we calculated the total resistance, but the reading here is going to be connected to this resistance that sits in series. Okay, cool. Then we have Vs is equals to 3, right, times the resistance in series is 3. I think it's considering this one. Oh, this one's in parallel. Okay, I understand. Okay, so we have a voltage reading when it's in series, and we have a voltage reading when it's in parallel. And we're looking for the ammeter when the voltage reading is in parallel. Okay, so when it's in series, we have 3 times 3, which is equals to 9, and then your V parallel is equals to 13.5 minus the 9 that we have here, which is then equals to 4.5. With that, we can then say R is equals to V over I. We have 4, right? Which is equals to 4.5 over I. So therefore, I is equals to 1.125. Okay. They say calculate the resistance of resistor R. Okay. So now we're looking for this. Okay. So how can we calculate that? We can say I is equals to 3 minus 1, because this is the total, okay? We calculated the total, but then we had to calculate the ammeter reading, okay, when the voltage is parallel, okay? So then we have I is equals to 3 minus 1.125, which is equals to 1,875 ammeter. Resistance is equals to V over I. So R is equals to 4.5 over 1 comma 875, which is equals to 2 comma 4. Okay, and then let me see if there's another question. No, I think that was the last question. It says the total. Okay. Okay, cool. So that is electric circuits. I think we have time now. I think I'm gonna maybe start with, or kind of do like a revision, because I think wave and sound is something that is done in term 2. So this will kind of just be like a quick revision. Okay. This is just a quick revision. We have a bit of time, so we're gonna go over question 6. Okay, cool. So now we've covered electric circuits and we've done two past papers. So now we're moving on to sounds and light. Yeah, sound waves. Okay. So they say a stationary sound, a stationary sound detector, a stationary sound detector placed at a certain distance records 52 sound waves per second from a moving source which emits sound waves of 48 hertz, which right emits a sound wave of frequency 48 for 480 hertz. Okay, so we have a stationary sound detector placed at a certain distance. So let's say maybe this is our sound detector. I don't know how. Right, so this is our sound detector, and it's detecting at a certain point, and it records and it's recording from somewhere. So it records 58 sound waves per second from a moving sound source. So here's our sound source and it's moving. Okay, we don't know if it's moving towards or if it's moving away, but it's moving from a sound wave, which emits a sound wave of 480 frequency. Write down, so 6.1.1, okay, so it says write down the frequency of the sound wave that the detector records in hertz. Okay, so that is given. So if it records a 580 sound wave per second, that is 520 hertz. Okay, it's waves per second, frequency is waves per second, so that is already given. So it's 580. 580. I hope you can see my 500. 520, my bad. Okay, it's waves per second. That is the answer. 6.1.2, it says define the phenomenon which explains the change in frequency observed. Observed. Define the phenomenon which explains the change in frequency observed. Okay. So they say so the answer is that the change in frequency or pitch observed or detected by a listener because the listener on the sound waves have a different velocity relates to the medium of sound propagation. So that's the phenomena. Okay, this is also definitions that you need to learn. Okay, it says that. So they're saying why is there a change in frequency? What's causing that? There's a phenomena that's causing that, and they says that it's because that the sound source and the listener have different velocity, right, relative to the medium of sound propagation. So the change in frequency or pitch observed or detected by a listener because the listener and the sound source have different velocity relative to the medium of sound propagation. Okay. Another answer would be that the change in observed or detected frequency as a result of relative motion because sound source and because between the sound source and listener. It's due to the fact that there's different velocities, due to the fact that there's relative motions between the sound source and the listener. So that's why there's a change in observed or detected frequency. Okay. 6.1.3, is the sound source, like I said, we don't know if it's moving towards or away. So now they're asking us, is the sound source moving towards or away from the listener? And then they say, give a reason for your answer. Okay. Is it moving towards or is it moving away? Okay. In this case, the sound source is moving towards the listener. Why? Because the detected frequency is higher than the sound frequency. Okay, so here's they say this the a stationary source sound detector placed at a certain point records 580 sound waves. Okay, um, from a moving source which emits a wave frequency of 480. Okay, so it's towards because the detected, right, which is this 520, is higher than the sound source, which is 480. Okay, sound, it's higher than the source frequency. So that's why it's moving towards. Okay, so then you have 6.1.4, They say calculate the velocity at which the sound source is moving. Take velocity of sound as 343 meters per second. Okay, so now we're looking for calculate the velocity at which the sound source is moving. Okay, so we're gonna say final velocity, final frequency. Frequency of the listener is equals to velocity plus minus velocity of the listener over velocity of the sound plus minus the velocity of the source. Okay, multiply all that by the frequency of the source. Okay, frequency of the listener. Okay, 520, 520. Okay, we're given the velocity, right? They say use the take the velocity of sound as 343. So you have 343, okay, over plus minus velocity of the listener. We're told that it's a stationary sound detector, so that is 0. Then we have 343 minus, so we know that it's moving towards the velocity of the sound. Okay, multiply all that by the frequency of the source, which is given as 480. Okay, so then we have Vs is equals to 26.38 meters per second. Okay, we have 6.1.5. It says, how would the wavelength of the sound wave produced by the sound source change? So how would the wavelength, okay, of the sound wave produced by the sound of the source change if the frequency of if the frequency of the sound wave became higher than 480. So how would the wavelength of the sound wave, okay, produced by the sound source, okay, change if the frequency of the sound waves became higher than 480? Write down only increase, decrease, or stay the same. Okay, what would the answer be? The answer in this case would be decreased. And the reason for that is that for a constant velocity or a speed of sound, if frequency increases, wavelength decreases. So for a constant velocity of speed, so if for a constant velocity or speed of sound, if the frequency increases, so if our frequency increases, then our wavelength will decrease. Okay. The spectral line from a distant star are observed to be three shifted. Explain the underlined term. Okay. So they say the spectral lines of a distant star are observed to be three shifted, red shifted. Explain the underlying term. So we're looking for definition, and here is that light from the star is shifted towards longer wavelength, so towards the red end of the spectrum. Okay, which indicates that the star is moving away from the earth. Okay, there's different lights indicate different things. So I think in this case we're looking for red shifted, so it says light from a star shifted towards the longer wavelength, so it's towards the red end of the spectrum, which indicates that the star is moving away from the earth. Okay, the next question says, write down one application of the Doppler effect in the field of medicine. This is also something that you can kind of remember, an easy one mark. So write down one application of the Doppler effect in the field of medicine. Here we have it's used to measure the direction and speed of blood flow in your arteries and arteries. Sorry. So it's used to measure the directions and speed of blood flows in your arteries and your veins. Another one, it's used to measure the heartbeat of fetus in the womb. Okay. So that is your Doppler effect. I think we can quickly go through another question as well. of question 6. Okay, so this is also Doppler effect, sound waves. So it says an ambulance. I can't see. Okay, there it is. It says an ambulance with its sirens emitting sound of a certain constant frequency approaches an accident scene at a constant velocity. So we have this ambulance, something quite happened, and it's emitting as it's moving, and it's moving towards this scene. Okay, this is the accident scene. Okay, nothing fatal. An ambulance with its sirens emitting sounds of a certain constant frequency approaches an accident scene at a constant velocity. So the ambulance is moving at a constant velocity. A stationary sound detector at the accident scene. So this is our detector. This is our sound detector. It's detecting the sound that's coming in. A stationary sound detector at the accident scene records a frequency of 2% higher than the actual frequency of the siren. Okay, so then they state the Doppler effect in words. So you kind of have to give the definition of Doppler effect. So Doppler effect is the change in frequency observed by a listener because the listener and the source have a different velocity relative to the medium of sound propagation. Okay. X6.2 explain why the detector records a higher frequency. So why is it recording a frequency of 2% higher? What's the reason for that? Okay. So when the source moves towards a stationary observer, the wave in the front of the sound is compressed. Okay. As a result. Okay, resulting in shorter wavelength and a higher frequency. So they are like this. They're quite compressed. Okay. In the front. Okay. So when a source moves towards a stationary observer, the wavelength in front of the source is compressed, resulting in shorter wavelength. So the wavelength here are quite short and a higher frequency. So that's the reason why the detector records a higher frequency. Okay. Then we have 6.3, which says calculate the speed of the ambulance. Take velocity of sound as 3.3 meters per second. So now we're calculating the speed of the ambulance. Okay. Same formula. Frequency of the listener is equals to the velocity plus minus velocity of the listener over velocity plus minus the velocity of the source. Multiply all that by the frequency of the source. Okay, frequency of the listener is given as 0.1.02. Oh, wait. Multiply, the frequency of the listener is 0.12 times the frequency of the source because it's 2% higher, right? Which is equals to 343. Okay, stationary is equals to 0 over 343. It's minus because it's moving towards. And then we have Vs. Multiply all that by the frequency of the source. Okay, these will cancel each other out, and we'll be able to just have one unknown, which is the velocity of the source, which will be 6.73 meters per second. Okay, I think we'll be able to just cover up until there. I think that's it. This is the end of the lesson. We're able to cover electric circuits and your Doppler effect or your sound waves.